student of Vivek, and since he's traveling today, I will give a guest lecture here. So, can the people hear me okay at the back? Okay. So today's lecture, we will continue our discussion on support vector machine, or SVMs. So in last lecture, we have discussed the hard SVM when the training set is separable. So in this lecture, I will give a very quick review of that, and then moving on to the new topic of today's lecture, which is soft SVM, and also how to optimize the SVM optimization problem. So let's review what we have covered already last lecture. So to remind you, the SVM is a linear classifier, so we have a hyperplane that separates data. In the hard SVM case, we are always assuming the training set is separable. So this is the setting we have been considering for hard SVM. And if the data set is separable, then there are more than one, actually infinite many hyperplanes you can find to separate the positive and negative data points. So which one do you prefer out of these infinite many hyperplanes? So in the SVM setting, what we want is we want hyperplane which gives you the maximized margin. So to remind you what's the meaning of margin, the margin for a hyperplane with respect to a data set is the distance from the closest data point to that hyperplane. So there are lots of hyperplanes, and we want the hyperplane which have the maximum margin. And so the hyperplane equation is defined by W and B's, and we only care about the size, so we have a freedom to rescale W and B's together, so you can multiply them by a constant. It doesn't change anything. So the mass formulation is in this slide. So the margin is defined by the distance from the closest point. So the distance from xi to the hyperplane is given by that equation without minimum. And then when you put minimum, that means you want a data point which is closest to that hyperplane. So the gamma is the margin for this particular hyperplane, which is specified by W and B there, right? And then we want find a W and B such that the margin is maximized. So we have a max in front of the min there. This is the hard SVM. So we want to maximize the margin, but we have a freedom to scale W and B together. So we want to use that freedom so if we multiply both W and B by a constant, it doesn't change anything. So why not we just restrict to the case where we want the closest distance is 1. So what I mean is the distance is given by this giant ratio. So we can always rescale so that we want the numerator to be 1 for the closest point. And then we want to maximize the margin. That's equivalent to minimize the denominator, which is the norm of the weight vector. So this is the formulation for hard SVM. In this case, maximize the margin. Gamma is equivalent to minimize the norm of the weight vector. So questions so far? So this is what we have covered in the last lecture. So yeah, this is the formulation of the problem. So we minimize the norm of the weight vector, W transpose W, subject to the constraint that the YWX is always greater or equal to 1, greater than or equal to 1. We use the freedom to rescale the weight vector to formulate the optimization problem in terms of minimization of the weight. So far, we have seen this in the last lecture. So from the next slide, I will talk about the soft SVM. So anytime if you have a question, you can just feel free to stop me. Yes?
So why do we have a greater than or equal to 1? Like, why can't we just have any kind of positive number?
Yeah, actually you can. You can have any positive number. It doesn't change anything. You can put 2 there or 100 there. But the importance is we want a positive number there. The exact value doesn't matter because you can always rescale.
So why don't we say greater than or equal to 0 instead of 1?
0, then you don't have any margin anymore. Basically, if you put 0 there, you're only requiring you classify the data correctly, but there's no margin.
But if you're saying greater than 0, like 0.5 still has a margin,
Yeah.
but it's less than 1, so it doesn't satisfy this.
Yes, but in that case, you can just double the weights so that it is satisfied as well, right? So as long as there's a positive number, you can multiply or divide that positive number to give you 1. But if you put 0 there, then it changed because there's no margin anymore.
Yeah.
You want a positive margin. So it doesn't matter whether it's 1 or 5, but for convenience, we just put 1 there.
Okay.
Yeah, so as I said, if you have questions, just stop me and ask. If there's no questions, let's move on to today's topic. So we have been talking about the case where the training data set is separable, but that's not always the case. Most likely, you don't know whether the data is separable or not. So what can we do in that case, right? If we're still using this same object optimization problem, meaning still using the hard SVM, objective and constraint, because the data set is not separable, that means such W and B does not exist at all. So it cannot find such a hyperplane which gives you margin bigger than 1. In fact, even if you don't require any margin, there's no hyperplane separating the data because the data set is not separable. So in this case, this optimization problem doesn't have any solution. There's no W and B you can find. So what we can do in this case? So let's look at some intuition from the geometric point of view before we go to the math. So here I have the same training data sets, but I have 2 more data sets in the circle there, the plus and minus, the 2 new data points which give us trouble. So if you all look at this, before that 2 data sets come in, our hyperplane classified these data sets very well and with a large margin. But with the new 2 data points, for the positive data, we can still classify it correctly, but it's within the margin, so it's so close to being mislabeled. And for the negative new data point, it's been corrected, it's been labeled incorrectly, so it gets a wrong label. So what we can do in this case? So there's no hope to find a hyperplane separating them perfectly with large margin. So we have to give up that hope. So we can just ignore these 2 points because the negative points will make the data not separable, and the new positive points will still separable, but it will make your margin very small. So we don't want to overfit to these edge cases like the positive and negative there. So we give up the hope so that we can separate them with large margin. So if we throw out these 2 points, we get back to the hard SVM case. The problem is which data points should we throw out, right? Given you a data set, you don't know which data is good or bad before you're finding the separating hyperplane. So you don't know which data point is bad. If you know, then you just throw it away, problem solved. Because we don't know, so what we do is we allow that for every data point, we give it a chance, a possibility to break into the margin. So let's look at what the equation means here. Originally, in the hard SVM case, if the data is separable, we require YWX is greater than 1. But if the data is not separable, we know we cannot find such time. So what we do here is, for every data point, we assign a slack variable Xi here. Xi is a Greek letter. You can think of Xi as how much this data point can violate this constraint. So instead of requiring YWX bigger than 1, we no longer require that. We require YWX bigger than a number less than 1. So we weaker our constraint in some sense. So we don't require it bigger than 1, but require it bigger than some smaller number. So Xi is how much, to what extent you allow this violation. So think Xi as a penalty if this data point is not outside the margin. So obviously we don't want very big Xi here, right? Because Xi is some kind of penalty. If the data set is separable, all Xi will be 0 because we know the constraint can be satisfied. There's no need for this loss for each data point. So now our optimization problem changed to the following one, where we minimize the sum of two terms. The first term, W transpose W, is just like before. We minimize the norm, which means we try to maximize the margin. Now the second term telling us that we also minimize the sum of all these penalties or all this loss for each data point. Because we don't know which data point is good, which data point is bad, we allow everyone has their own penalty if they violate the margin constraint. But then we want to minimize this penalty. We want to minimize the loss. We want to minimize to what extent you break the margin constraint. So does the second term intuitively make sense here? The sum over Xi. This, I think if you haven't seen this before, it takes some time to wrap around and think about this.
So do we allow different Xi for every example?
Yes.
Okay.
So different examples have different Xi. For example, if a data point is very far away from the hyperplane, whatever hyperplane you consider, then Xi is 0. So because in that case we don't need that. We don't need that thing, right? It's already satisfied the margin condition. Only for those bad data points that we allow some positive Xi, give them some room to violate the margin constraint. So that's why we want also at the same time minimize.
So this Xi will be increasing the dimension of this organization model, right? Because Xi is a variable, we can change.
Yes, Xi is extra variables we introduce into this problem. For each data set, for each data point in the data set, you have a Xi. So it's increased a lot of new variables, increase the dimensions, yes. But this is not what we eventually optimize. So we will later on introduce another form which is equivalent, but has less dimensions, yes.
So intuitively, the slack variable is how far into the wrong label area you are?
Let me draw a picture. So the slack variable. So suppose this is my hyperplane. You have a bunch of positive data, negative data. Let's say this is the margin. For these data points that outside the margin, we don't need Xi. Xi is 0, just like the hard SVM case. But if the data point is labeled correctly but within the margin, then we need a Xi here. So the Xi is actually the distance from the data point to the margin plane here. So for the distance from the data point to this margin is Xi. So how much violation you introduced into the problem. So if the positive point go to the other side, you give it a wrong label, the Cassie is very large. So the distance here is Cassie. So think about Cassie as how much you need to pay in order to violate this margin constraint. And same thing for the negative point. So if the negative point go to the wrong side, so the Cassie for the negative point is the distance to this constraint plane.
But your margin's going to be changing as you learn the weight vector, right?
Yes. So we learn the weight vector and the Cassie simultaneously. So we have a joint minimization, not joint, but we minimize over the sum of two terms. Right? We want to find both things. So in between these two terms, there is a constant c. So this c can be changed for any positive number. Any positive number can be put there. The purpose of that constant is by treating off the relative importance between the two terms. So if, for example, c is very small, close to 0, let's say, then you are only minimize the weight vector. So you are looking for maximizing the margin without considering any margin constraint. That means you basically throw away all the data points because you are thinking all data points are bad. You just don't want to consider them. So you end up with minimizing the weight vector, which gives you W equals 0 if C approach 0. So you are looking for generalization, but you forget about all the data points. On the other hand, if C is very big, close to infinity, let's say, then the first term doesn't matter anymore. So we don't care about any generalization. Remember, large margin from the first term means generalization. So if C is big, we don't care about generalization. We only care about this particular training data set. We want to make sure that for this data set, we can either separate them perfectly, or if not, we are trying to minimize the penalty we pay to violate this margin constraint. So by tuning C, you can just trade off to the relative importance of generalization and overfitting to the data. So typically C will be chosen by using something like cross-validation. Okay, so this is the formulation for soft SVM. And the difference from the hard SVM is we allow this to see here. So we have a weaker requirement. We allow it to break into the margin. And in this case, pay attention that we are also minimizing Cassie, not only the weight, but we are also minimizing Cassie here. Okay, so I have already explained these slides. The first term is generalization. The second term is the fitting the training data sets. And C can be chosen by using cross-validation. So as just one of you have already asked, introducing Cassie makes problem more complicated because now we have a much more larger problem with more variables to worry about. So what we can do is we can slightly rewrite this to get an equivalent optimization problem, but it turns out easier to solve. So let me show you this equivalent minimization problem, and I will explain why it has this form. So the claim is these two optimization problems are actually equivalent, but the second one doesn't have any constraint anymore. It is an unconstrained minimization. The second term is a max function. Just choose the max between the two. So let me explain how we get from the first optimization problem to the second. So the first optimization problem has two constraints. the first one is yi wxi bigger than 1 minus ci. The second one is ci is positive or 0, right? So the first one can be rewritten just by rearranging the terms. It's 1 minus yi wxi. So I didn't do anything except rearranging the terms. This is the equivalent. And I still have the second one. So I can go from here to here. The next step is by observing the fact that the ci is bigger than these two things, right? Bigger than this one and bigger than this one. So if ci is bigger than both of them, it has to be bigger than the max between these two. So the third formulation is equivalent to the second because if you're bigger than both things, you're bigger than the bigger one of them, right? And vice versa, if you are bigger than the bigger one of the two, you're bigger than both of them. So this is equivalent. The c is bigger than the max between 0 and 1 minus ywxi. So that's what we have here in the second term. So we replace c by the max function, and we get rid of the constraint equations. So our new optimization problem is formalized this way. The first term is still pushing for max margin. The sixth term coming from the constraint equations, and it can be interpreted in a way that I will talk about in the next slide. But so far, any questions? How we can get from the first one to the second? Okay, so if there's no questions, so let's look at the second optimization problem, the second formulation of the same optimization problem. Let's try to interpret what this equation means. Okay. So we know the first term tells us we want to maximize the margin. And we know the second term coming from the constraint equations. So the max function have two components, right? So either 0 could be bigger or 1 minus ywx could be bigger. So let's consider them separately. So first case, if 0 is bigger, I mean if 1 minus ywx is less than 0, this is the old case for hard SVM. So ywx is bigger than 1. The max between the two is just 0. There's no penalty. This is the case we like. And this corresponding to the data points outside the margin. Now, if 1 minus ywx is less than 0, so that means ywx is less than 1. No, if 1 minus ywx is bigger than 0, so the max coming from the second term, that means ywx is less than 1. So in this case, there are two subcases, right? So if ywx is between 0 and 1, that means we still correctly label the example, but this example is within the margin. On the other hand, if ywx is less than 0, that means we labeled this example wrong. So y and wx have the different sign, we make the wrong prediction. So in either case, we have to introduce a penalty which equals to y minus wx. So you can think about the second term as a loss function. So this is what we call the hinge loss function. And it's called the hinge loss because of, if you look at the shape of this function, it looks like a hinge. So looks like this. I don't think the color is very clear. So let me point. So this line is the hinge loss, whereas this step line, like a step function, is 0, 1 loss. So yeah. So we know 0, 1 loss. That means if we predict it correctly, there's no loss. The loss is 0. If we make the incorrect prediction, the loss is 1. So for every example, you have either 0 loss or 1 loss. And for the hinge loss case, this is what we have in the SVM world. We not only requiring YWX is bigger than 0. Remember, YWX bigger than 0 just means you make the correct prediction. But we require YWX bigger than 1. So we not only require you make a correct prediction, but we want that the data points outside the margin. So if YWX is bigger than 1 here, the loss would be 0. On the other hand, if YWX is less than 1, then you have to introduce a loss. And the smaller the YWX, the bigger the loss. So as you move away from 1, go to the negative side, you have more and more loss. And the loss is linear in terms of YWX. So we can interpret the SVM objective by using this hinge loss. So let's go back to the objective function. First term is maximize the margin. The second term is penalty we want to minimize, or the loss we want to minimize. So this is an example of a general learning principle, which is called the risk minimization. So the risk minimization, risk is just the same thing as loss. The same meaning means we try to minimize the loss over the training data sets. Yes.
I have a question. So would our update, would that look something like a gradient descent then? We would descend towards the least penalty?
Yes, exactly. Okay. And I will cover that in the later part of this.
Okay.
We will go there. Okay. So as I said, this SVM objective is an example of a general learning principle because we define a loss for the training set and then we just try to minimize the loss to find a way to give us the minimum loss value. So learning is just find the hypothesis which has the lowest loss on the training data set. But if you only care about making good prediction on the training set, we know already that that's overfitting, and we also want to get good generalization. So we can put another term which is called a regularizer or regularization and minimize both the regularization and the loss or empirical loss. So in this case, learning is find the hypothesis which minimizes the sum of the regularizer and the loss of the training data. So go back to SVM. The first term is one example of a regularization term, one of the regularizer. And the second term is one example for empirical loss. So the first term here is called the L2 regularization. In this SVM case, it's pushing for maximize the margin, and it helps to for generalization. And there are other possible regularization terms possible, but in the SVM objective we derive, it has this W transpose W form, and it's a very common regularization term. The second term is the loss function, in this case the hinge loss. We want to minimize the loss on the training data set. This is how you can fit the training data sets. And there are also other possible loss functions, and perceptron loss are one example. And later in the semester, we will cover another loss function which is called the logistic loss. But this is example of the loss function, the hinge loss in this case.
Did you say that the first term, the regularization term was, you said you called an L2 function?
Yes.
So where does that term come?
That term comes
Yeah,
from?
yeah, L2.
Um,
I've heard it before, I just wanted to know.
L2 is just because we are minimizing the second order, basically the sum of the components, W1 squared plus W2 squared
Oh,
plus
okay.
W3 squared.
Okay.
I see. Okay. Okay, so yeah, the constant C just trade off between the importance of two terms. It can be chosen by using cross-validation. Why it is still not stable here?
Is there a general range for the value of C, like between 0 and some number, or do you just have to?
Typically, we don't have a general range, but when you're choosing it like in the logarithmic scale, like 1, 10, 100, 1,000, and you use cross-validation to choose that.
So it's always greater than 1?
It's always greater than 0, but
Oh.
could be like 0.1. So it's a positive number. Okay. Let's go. So we have formulated the optimization problem. The next step is how we solve this optimization problem to actually find the weights W and B's. So let's try to focus on how to solve the optimization problem. And it turns out that this optimization problem has an important property, which is called the convexity, that will help us a lot for optimizing it. So let me introduce what is the meaning of convexity here. If we know the function is convex, then it will be much easier to optimize. So this is a slight detour for introducing the meaning of convex functions. So mathematically, the convex function is determined using that equation, but let's not look at that right now. So intuitively, for example, if you, in the 1D case, the convex function is a function, the shape of that is just like a ball. It's just layman's term. If you think about intuitively, the function shaped like a ball. What does that mean is, for any 2 points, U and V, you join using a line segment connecting U and V, and the function graph is always lie below the line segment connecting the 2 points. And that's one interpretation from the picture. Another interpretation from the picture is by looking at the tangent lines. So if you have a convex function, at any point you can just draw a tangent line such that the tangent line always lies below the function. And let's look at some examples. So the linear function is convex. You imagine you have any two points, you connect them, the function lies below. In this case, they are overlap, but still overlap or below. So that's convex. The second one, x squared, is a parabola. It's obviously a convex function. It's just like a ball. If you draw a line, then the function will be always below the line, right? And the third one is interesting. It's actually the one where we use in SVM case. So the max function is convex if the components inside max is convex. So we know that 0 is a constant. It's just like a straight line, horizontal line is convex. x is a line like that. So if the components inside max is convex, then the max is convex. So the graph for this function is in that shape. If x is less than 0, it's 0. If x is bigger than 0, the function is x. So this is convex, right? The function always lies below the line connecting any 2 points. So imagine you just connect any 2 points of the function. The function graph lies below that. In higher dimension, for example, in this case, this is a quadratic equation. And if you imagine you just connect any 2 points, the function is always below. There's nothing above that line. Okay, so this is a geometric view of the meaning of what does convex means. Not all functions are convex. Okay, so let's actually go back to the mathematical definition, since we have already seen some examples. So the definition is an inequality. The first side, we have a lambda parameter that's between 0 and 1. So let's look at the left side. If lambda is 0, lambda u plus 1 minus lambda v is just v. And if lambda is 1, that term is just u. So by changing lambda from 0 to 1, you are moving from u to v. So what we are doing here is by changing lambda, the x point moving in between these 2 points. The function value f of that is the point on the blue curve. And that one is always less than or equal to the value given by the line segment. So at the right side, you have fu and fv, and similarly you have the same lambda parameter. We are changing the position, moving from u to v, but whatever that parameter is, at any point, the function value, the blue curve, is always below the right curve. This is the meaning of that inequalities. And that's the definition of the convexity. And this definition works in any dimension. The picture just shows you one dimension, but the math definition is a general definition. So u and v could be high dimensional functions. And this is the examples we have talked about. And there are some examples for non-convex functions. For example, the box on the left. These are just the opposite case of convex function. In this case, they are called concave functions. So if you imagine you connect a line connecting any 2 points, the function is always above that connecting lines. So if fx is convex, then minus fx is concave. If fx is concave, then minus fx is convex. So you just flip it upside down and change between convex and concave. The box on the right, it gives you some example that is neither convex nor concave. So you connect 2 points. Some part of the function lies above the line, and some part of the function lies below the line. I forgot to mention, in the concave case, we just flip the definition. In the convex definition, we have less than sign. In the concave, we have changed it to greater than sign. So why convex functions are good? If we don't know the convexity of the function in general, if we want to find the minimum, a natural thing to do is try to find a point where the gradient is 0. The gradient is like a generalization of the derivative in high dimensional case. So if you find the gradient is 0, that's a possible candidate for minimization point. But it's also possible to be actually a maximum point. So in general, we don't know whether a point with 0 gradient is maximum or minimum or even saddle point. For convex function, if we know that at x point the gradient is 0, then we know that it's guaranteed to be a minimum. And not only a minimum, it's a global minimum. And this is only true because the function is convex. So a convex function that's you only, like a ball, it can only have one local minimum. No, it can only have, the local minimum are always global minimum. So there's not possible to have local maximums. So if we try to find a point with 0 gradient, then we will know that we arrive at the minimization, the global minimization point. That's why convex function is good if you want to minimize this function. So how to solve this minimization problem? This function is in a form which is called quadratic programming. Quadratic programming is just a function, the objective function is second order, like this case, and it can or cannot have any constraints. In this case, we don't have any constraints. And there exist quadratic programming solvers that we can use, but they are very slow. So what we use in our case is we will use stochastic gradient descent, which turns out to be much faster to solve this, to find W and B than quadratic programming. But before we talk about this stochastic gradient descent, I have to introduce this more general thing called gradient descent. So if you want to minimize a function, let's call it JW, J of W. W is a vector. J of W is a scalar. You want to minimize that. So one thing to notice is that the gradient is the direction, the gradient points to the direction where the function value increases the most. So the gradient is a vector. Each component is a partial derivative. For example, if we are in the three-dimensional space, so the gradient is a vector containing 3 components. And the direction of that gradient is pointing to the direction where the function increases the most. Since we know the gradient has this property, and what we want is trying to find the minimizer, we are trying to go to a point with smaller value. That means the natural thing to do is we going in the opposite direction as the gradient. So in 1D case, the gradient is just the derivative. It could be either pointing to the right or pointing to the left. You just, in 1D you only have 2 choices. The gradient pointing to the increasing direction. So we are going backwards. In this example, suppose we have some initial value W0, and then you see the gradient pointing to the right. That means you want to go to the left, moving a small step to W1, and then calculate the gradient, which is the slope of the tangent. And it's still pointing to the right, so you still go to the left. You keep going. So this is called gradient descent. So you're always going to the direction that is in the opposite to the gradient direction. So if we overshoot, let's say we are at W3, we go to the left, to a large step at the left part, and then the gradient will be pointing to the left at that time. So we will move to the right to come back to the minimum. So we're always going backward in the opposite direction as the gradient. This is the intuition of the gradient descent, and this is the algorithm. It's very simple. First, we just initialize W0, and then because we want to minimize J of W, we calculate the gradient, which we call nabla J of W. This upside down triangle is called nabla. The meaning is gradient. So we calculate the gradient at that point, and then at the next step, you're just going in the opposite direction. So the t plus 1 step, you just go from the t step by moving negative direction. So minus lambda j is going to the negative direction of the gradient. And r is a scalar, so think about r as how much distance you want to go in the direction opposite to the gradient. So r is a small scalar parameter. In this case, it is called learning rate because if r is bigger, at each step you make a larger step, make a larger leap. If r is smaller, then you just very conservative, just move a little bit. Okay, so this is the gradient descent algorithm. But one drawback for this algorithm is to calculate the gradient, we have to calculate the sum of a lot of functions. So remember the original objective function, j of w. There is a sum there. It's sum over all examples in the training set. So when you calculate the gradient, you also have to, for each training data point, you have to calculate the gradient separately and sum them all together. So there is a lot of work to do in every single step. It's very slow. For large training data set, it does not really scale. So this is the intention for us to introduce stochastic gradient descent instead of just plain gradient descent. So let me go over what's the meaning of stochastic gradient descent. It's quite similar to gradient descent. We have a training set given to us, xi, yi, and then for every epoch, you can think about epoch like we iterate through the data set several points. So every step, you just random sample a data point from the training set. You just choose uniformly random from the data set. Get 1 point, and pretend that your training set only containing that one data point. So now your objective function only contains this one data point. Like this equation, there's no sum over I anymore. There's only a single example. Instead of consider the sum of all possible examples, we just sample one of them. And then this is our new objective. Calculate the gradient of this new objective, and do the same update as gradient descent. So you do this over and over, and then finally you will return the final W. This is the meaning of stochastic gradient descent. This is just a basic framework. Once we have that, I will go into the individual pieces to explain more specifically how we do this. But does the general framework clear at this point? So it's very similar to gradient descent. The only difference is just pick one example and forget about all the others. And then the next time, because you are doing random sampling, you hopefully, most likely, you will get another example and another example in the next step. So you do this multiple times, you converge to a final value. So there's a theorem which says that this process, if you choose the learning rate, the small coefficients in front of the gradient, the gamma t, if you choose that wisely, this objective function is guaranteed to converge. And this is because the function is convex. When you have a convex function, each time you just go through, each time you just try to go to the opposite direction, you will arrive at the minimum point. So here are some intuitions. Comparison between gradient descent and stochastic gradient descent. So on the left, this picture is a contour plot for a 2D function, right? So we have a 2D function. The contour plot just means for each contour, they all have the same function value. So you can think each ellipse has the same value. For example, this line all have function value, let's say 100. The next line all have value 90, and the next 80. So as you get closer and closer to the minimum, the function value decrease. So this is the meaning of the contour plot. And then the gradient descent is just starting anywhere. So for example, in this case, we are starting here. And each step, we make a small step towards the minimum position by going opposite to the gradient direction. So eventually we arrive at the global minimum. On the right side is still a contour plot for the same function, but in this time we are doing stochastic gradient descent. So the purple lines, we are starting from here, and we are going in the opposite of the gradient direction. But remember, this time the gradient is not the true gradient for the whole function. The gradient is estimated from only one example, right? So at each step, there's a possibility that you're actually going in the bad direction, because that example might be not giving you a good estimate of the true gradient, which means at each step, you could actually increase the function. But eventually, if you do this truly uniform random, it will converge to the local minimum. And there's a theorem guarantee about that. So that's why the purple line looks a lot messier than the red line there, but it will arrive at the same position. So remember that even though this looks like much nice, every step is very expensive because the gradient calculation involves sum of a lot of terms. If you have a million trillion example, the gradient calculation involves sum of a million terms. So even this looks a lot nicer, one step costs you a lot more than the other case. So this looks not very messy, but every step is very easy. So you just do a lot of steps and you will arrive. And practically this stochastic gradient descent will be much faster. And if you are curious, the red line here is, I think, is the average of the weight vector at each step. So just like you can do average perceptron, you can also do average stochastic gradient descent. I don't think we need to worry about average here for our class and for our assignment. Just let you know about that. You can also do average. Okay, so this is the stochastic gradient descent algorithm. This is the original form. Notice that the step 1, 2.1 is pick a random example. And the only thing left is how can we calculate the derivative and make an update. We haven't covered about that part yet, and I will cover that. So how to calculate the derivative or gradient when the function is not smooth, right? The max function has a kink. It's not differentiable at that point, so how can we calculate that? It turns out that we need to introduce a general idea, slightly general than gradient, which is called subgradient. So let's go back to, let me remind you what the gradient is, right? The gradient is just the slope of the tangent line in 1D in this picture. And in high dimensional, you can also find a tangent. In that case, it might be a line. It could be a plane or hyperplane. But that hyperplane always lies below the function itself. And if the function is smooth and differentiable, in that case, it turns out there's only one such tangent plane exists. So this is what happens when the function is smooth and differentiable. If the function is not smooth, not differentiable, we can still define subgradient by saying that if we can find a tangent that's lies entirely below the function, then the slope of that line is subgradient. So this picture only shows you 1D case. The right line, this function is smooth. So it has this tangent line, this gradient. This one is an example where it contains a kink point, x2. So if you look at this picture, x2 is not a smooth point. And x1, just like before, is smooth. So for smooth point, you can find only one tangent. And the slope of that tangent gives you the gradient. And in fact, it can be seen as a definition. If you can find a vector g such that this inequality holds, then g is a gradient or a subgradient. So in the first case, you can only find one such g because there's only one tangent. If you just perturb it, it will not be tangent anymore. But in the second case, x2 point, there are infinite many tangent lines or tangent planes, hyperplanes in high dimension. So you can find infinite many of them. Each one of them defines a subtangent. So in this case, G2 and G3, the slope of these two lines are both called the subgradient at this point. So that's not clear. Need more explanation. Yes.
Couldn't we just do away with the idea of there being infinite subgradients by using the approximation of the derivative and just sampling f above, before and after any x we care about?
What do you mean by?
Well, just by sampling f before and after x2 and taking the slope of that line. And we just pick some delta, and that's always the delta for our approximation of the derivative.
That's essentially what we are doing here.
Okay.
Because this is that's essentially what we are doing, because if you make this one continuous, smooth, it will be a function like that. And this one, just imagine you extend it smoothly. You have two smooth functions intersect at that point.
Okay.
And you can find two derivatives, two tangents for those two functions. It defines the region where you can find the subgradient.
Okay.
And what the function here is the max between that two. That's why this works, because the max of two convex functions is convex. That's essentially what happened here.
Okay.
Okay. Yeah. So just remember that the subgradient is just like gradient. Is the slope of this line that completely lies below the function line. So it turns out that we can use subgradient descent instead of gradient descent. Okay, so let's calculate the subgradient for the SVM objective. So the first term is easy. So the second term gives us trouble because we have a max function. And we consider two separate cases. If the max coming from 0, that means if 1 minus y(w(x) is negative, the first line gives us the max is just 0. We only have the first term, so the derivative or gradient is just w. On the other hand, if y(w(x) is bigger than 1, the max is just 1 minus y(w(x). So the gradient would be, in this case, would be minus cyx, right? You just take the coefficient in front of w for the second term. So we solve the max by separating two different cases and find the gradient for each different cases. And the gradient for each different cases are the subgradient for the overall max function. So let me repeat that. So the max function has two components. We separate two cases and solve the gradient for each cases, right? Because each piece are smooth. They have a derivative. They are differentiable. So we solve each pieces, finding the gradient And the gradient for each pieces gives us the subgradient for the overall mass function. So the subgradient for the overall mass function has two cases. In the first case, just W, only coming from the first term. And in the second case, the subgradient has two components. One is just still W, the second is just derivative with respect to W, which is minus C by X. It's just the coefficient in front of W in the second case. So we know the subgradient of the objective function. Okay, so we can do a stochastic subgradient descent. Initialize all the ways W. And then for each epoch, we are iterating through the data set multiple points. We select one example, and we do the gradient update. So this is what we have before, right? W changed to W minus gamma times the gradient. Since we already calculate the gradient, we just plug in the gradient in. And we have two separate cases. We have two separate update rules for the W. So this is the new SGD algorithm where we already calculate the subgradient so that we have the update rules explicitly written there. And gamma, as before, is learning rate. And notice there's one difference from the first SGD algorithm. In the first SGD algorithm I show you, we are random sample a data point from the training set, right? Each time we just pick randomly from the data set, do the update, and then next time we pick another random sample, do the update. In this case, we are not doing random sample, but we're shuffling all the data sets. So what we have here is, we have all training set, yes.
I'm wondering, how do we know that it does converge?
It does converge.
Like, do we check for convergence, or do we just pick a fixed capital T?
You can do both things. For example, you can check how the objective value at each step actually, does it decrease? Does it converge? It turns out to be stable. So you can check that. And also you can count how many steps, and let's say you have a maximum number of steps you are willing to do, right? If you go beyond that, you just stop, you lose your patience. Yeah, so you can do both things, and you can combine those things. Okay. So here, instead of random sampling, we consider all the training set together, and we just look through every example in the training set. And it's better to shuffle the training set every time, just to mimic the process that we are doing random sampling. So this time, we don't do random sample, but we shuffle the whole training set, and then after shuffle them, we just looping every example in sequence. This is like doing random sampling, but not exactly. We are mimicking that process. And by the way, this is the version that you are going to implement in your next homework, I believe. So I have to talk about everything. The only thing left is this gamma t, the learning rate. So there are some theoretical studies, like how to choose the learning rate. And it's been proved that the gamma t should get smaller and smaller, right? As you are approaching the minimum, you want to reduce the step, right? At the beginning, you are far away from the optimum. You can make relatively larger step. But as you get closer and closer, you should reduce this learning rate. You make smaller step once you close to the optimal points. So the step size is a function of the step t, so you don't use a constant. At each step, you reduce the step size a tiny bit. And the theorem shows that we should use step size which is square summable but not summable. So what's the meaning of that? So here is the example. In the example, gamma t is a function of t, where t is just a step, like the first step, second step. Gamma 0 is the initial value. You can just pick any initial value. For example, you can pick gamma 0 like 1, for example. And c is the constant trading off two terms. Remember, there is a c in front of the hinge loss. So trading off between generalization and the fitting the data set. So as you can see, as t increases, the whole gamma t will decrease, right? The t is in the denominator. And if you sum this thing from t, goes from t equals 1 to infinity, this will be diverged. It will goes to infinity also. But if you sum the gamma t squared, it's not, it will converge. It will not go to infinity. This is the meaning of square summable and not summable. But you don't need to worry about that theorem. You can use this definition in your homework when you implement the SGD algorithm. And again, this gamma 0 and c are hyperparameters. As always, you can use cross-validation to choose gamma 0 and c. So here are some theoretical results about convergence property. If we want our objective function to close to the minimum with accuracy epsilon, then the number of iterations we need for gradient descent is on that order. So nd log 1 over epsilon. N is the number of examples in the training set. When you compare that number to SGD case, there's no n there. So it does not depend on the number in the training set. It converges faster than gradient descent. So especially for data set which is very large, calculating gradient is expensive. So in that case, SGD is almost always better than gradient descent method. Okay, so this is a comparison. So this is the SGD I just show you. Same thing, nothing different. This is the version you will implement in your homework. And then let's take a look at this update step and compare it with the perceptron algorithm that you have already known. So the perceptron algorithm says, a new example coming, if we are making the wrong prediction, y and wx has different sign, then we're wrong, we need to make an update. That's the perceptron update rule. And compare it with the SVM update rule, you can see they are pretty similar. The two algorithms are very similar to each other. There's a tiny change for the update rule. And this suggests that this is the perceptron algorithm can also be viewed as a regularized risk minimization problem. But in that case, there's no regularizer. If we define perceptron loss like this one, max 0 minus YWX, if we define a loss function like that, just like we define hinge loss in SVM, and we are doing loss minimization using subgradient descent, and you calculate the subgradient for that function, you will find out that the update rule will be the same as the perceptron update rule. So you will recover the perceptron update rule just by using SGD with the perceptron loss. So both perceptron loss and hinge loss can be used when you are doing loss minimization. If you are using perceptron loss, it will give you the perceptron update rule, which is the same as perceptron algorithm. If you are using hinge loss with the regularizer, you will recover the SVM algorithm. So they are in the same general framework. Okay, so this is the summary of everything I have talked about. So in SVM, we try to minimize the regularized hinge loss, and to solve it, we can use the old method like quadratic programming, but what we actually use, which is much faster, is stochastic gradient descent. Because the function is convex, gradient descent and the stochastic gradient descent both guarantee that we can arrive to the global minimum. But the gradient descent is not fast because the gradient calculation is very expensive. The stochastic gradient descent is much faster because the gradient calculation is very simple. Each step you use a simple update loop. So even though the SGD takes much more number of steps, but because the step itself is very easy, it tends to converge much faster. So it's much faster than gradient descent. And I think this is the end for this lecture. And then in the next lecture, Vivek will talk about the dual form and also kernels. And also the question why this is called support vector machine. What's the meaning of support vector? And that will be the topic of the next lecture. So I think we still have 5 minutes. So if you have any question, need any explanation, I can answer.
So,
Yes.
why do we need to reduce the learning rate? Because with every step we take, the gradient reduces because we're going towards a minimum. So every step is anyway smaller than the previous step. Because we're getting a lesser value of the gradient.
Oh, yes.
But we still need a reducing learning rate. It's like a double optimization.
Yes, yes. That's a good observation, actually. The gradient is also reducing at each step. Because eventually we will arrive at a point gradient is 0. Yeah, this is a good question. I don't know why we need to do both things. But this is practically which give us better results. And also there are theory prove this about we need to reduce to get the convergence guarantee.
And also, so do we reset the learning rate for every epoch? Or?
No.
Okay.
No.
Okay.
Yeah, this is very important. Probably I should emphasize this. It's not shown here. Gamma t is given by that equation I've shown you. And it changes with every t, but you don't reset, right? You initialize at the very beginning, and then you always decrease this. There's no reset at the beginning of each epoch. And that's very important in your implementation. Yes. Any other questions? Yeah, okay. So if there are no questions, then I think that's it. And so I think Vivek will see you next week.